This is lesson 10 in the syllabus, integration by parts, which is a very useful and very important technique to integrate. So substitution, which is the previous technique we used, was based on the chain rule in differential calculus. Integration by parts is based on the product rule. So let's recall the product rule for the derivative of two functions. If you have two functions, u and v, and we want to differentiate with respect to x, that's u times dv dx plus v times du dx. Or I can write that as uv prime plus vu prime. By the fundamental theorem of calculus, every differentiation formula has a corresponding integration formula. So if we look at a function which is of the form uv prime plus vu prime, the integral of uv prime dx plus, well, let me write it like this. The integral uv is the indefinite integral or the antiderivative of uv prime plus vu prime dx, which I can write as the integral of u v prime dx plus the integral of v u prime dx. And some people like to write this as follows. V prime dx is dv dx dx. So as a kind of shorthand, we can write that as dv, just as if these canceled. And u prime dx, which is du dx dx, we can just write in kind of a shorthand notation as du. So uv is the integral of u dv plus v plus the integral of v du. And if we rearrange this, we get the formula for integration by parts. It says the integral of u dv is uv minus the integral of v du. So this is a beautiful formula that has many, 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 many applications. Let me do a couple. And I'll start doing examples that are in the text. This is example 1. Suppose we want to integrate the function x e to the x dx. That looks kind of complicated, so we hope we can put it in this form. We can think of having a kind of a table. U equals v equals u prime equals v prime equals. So I have u dv or uv prime. So suppose we set u equal to x and v prime equal e to the x. Then the integral of u dv, or the integral of u v prime dx, that's the integral of x e to the x. That's what we're interested in. Now, if u is equal to x, u prime is 1. If v prime is e to the x, the antiderivative is just e to the x. So that by our formula, this is going to equal u times v, x e to the x, minus the integral vu prime, e to the x dx. But we know the integral of e to the x, it's e to the x. So we have x e to the x minus e to the x plus a constant. That's pretty quick. Let's just check. The derivative of x e to the x minus e to the x, the derivative of x e to the x is 1 times e to the x plus x e to the x minus e to the x. These cancel. We get x e to the x. So that checks. So somehow the integration by parts formula allowed us to go from the integral of x e to the x, which is hard, to the integral of e to the x, which is easy. And that's why we could do the integral. Let's look at another example. Again, these look hard, but integration by parts makes it a lot easier. So I like to make this little 2 by 2 table. This is the product of these two functions. So let me let u be equal to x squared and dv, or v prime, be log x. So the derivative of x squared is 2x. The antiderivative of log x, that's hard. I don't know what that is. So this doesn't seem to help. I would have to find the antiderivative of log x, and I don't know that. What is the lesson? Well, the lesson is practice and experiment. So choosing x squared and as u and log x as dv didn't work. Let's try it the other way around. Suppose we make u equal to log x and dv equal to x squared. So let me just cross that out just to make sure we know that didn't work. So now I'm going to try u equal to log x and v prime equal to x squared. The derivative of the log is 1 over x. The antiderivative of x squared is 1/3 x cubed. So by the formula for integration by parts, this is u times v, 1/3 x cubed log x, minus the integral of uv prime, 1/3 x cubed, 1 over x dx. This is equal to 1/3 x cubed log x minus, take the 1/3 outside, the integral of x squared dx. 1/3 x cubed log x minus 1/3, and the integral of x squared is 1/3 x cubed plus a constant. So we get 1/3 x cubed log x minus 1/9 x cubed plus a constant. This is example 2. Let's do another example, which is a little bit trickier. We have the integral from 0 to 1. This is now a definite integral of the arc sine of x dx. Now you might say, well, how can we use integration by parts here? Because in the integration by parts formula, you always start with the product of two functions. You always start with something of the form the integral of u dv, or the integral of u v prime dx. And the answer to that riddle is, well, everything is 1 times itself. I can think of this as 1 times the arc sine of x. If I let u equal arc sine of x and v equal 1, and v prime equal 1, the antiderivative of 1 is x. Derivative of arc sine is 1 over the square root of 1 minus x squared. So this is equal to u times v, x, arc sine of x, minus the integral of v du. And this isn't as hard as it looks because that should be an easy substitution. You have the integral of x over the square root of 1 minus x squared dx. That's like a half times 2x. By that u equal 1 minus x squared, du is minus 2x dx. Let me make this a minus and a minus. This is minus 1/2. The integral of minus 2x dx is du over square root of u. It's minus 1/2 the integral u to the minus 1/2 du. Add 1, you get a half. Take the reciprocal, you get 2. So this is minus the square root of u plus a constant, which is minus the square root 1 minus x squared plus a constant. So I plug this back in here, I get arc sine of x minus the square root of 1 minus x squared plus a constant. X arc sine x. Oops. Oh, yeah. Minus the integral. The integral is minus, makes this a plus. Plus. That's the answer. I'll do one more example. And then I'll do a lot more in our Zoom problem sessions. So sometimes you have to use integration by parts repeatedly. This is example 4. The integral of x squared sine x dx. So we might let u equal x squared and v prime equal sine x. In that case, the antiderivative of sine x is minus the cosine, and the derivative of x squared is 2x. So we get minus x squared cosine x minus the integral of 2x times minus the cosine. Makes that a plus. So, but we still have to do this integral. Let's do another integration by parts. If we have to integrate the integral of x cosine x dx, if I let u equal x, du dx is 1. If I let v prime equal the cosine, the antiderivative is the sine. So this is simply x sine x minus the integral of the sine of x, which is x sine x, and the antiderivative of the sine is minus the cosine, which makes this a plus. So we take this and plug it into here. We get minus x squared cosine x plus 2 times x sine x plus cosine x. So we have minus x squared cosine x plus 2x sine x plus 2 cosine x plus a constant. That is integration by parts. It's a beautiful, concise formula and very, very, very useful. The integral of u dv is uv minus the integral of v dv. So this is another one of the really great formulas from Calc 2. That's it.